The Tunguska event is often introduced as a mystery with a familiar answer. On June 30th, 1908, a major explosion devastated part of the Tunguska region. The leading scientific framework is not a hidden weapon, an exotic force, or an impact that somehow erased its own crater. It is a cosmic body depositing destructive energy in the atmosphere. That explains why a conventional surface crater is not required. But it does not recover the object itself. It does not give us one certain composition, one measured path, one observed breakup sequence, one exact altitude, or one final energy value. Those details come from reconstruction. And that is where the real Tunguska problem begins. Not with the absence of an answer, but with the distance between a strong, broad explanation and the precise history we still want it to reveal. The event lasted moments. The record of it was assembled over decades. Accounts associated with Tunguska describe intense light, sound, shock, and violent ground effects across a wide region. But these reports do not all have the same evidentiary weight. Some records were created close to the event. Much of the testimony, however, was collected later, sometimes decades after 1908. Locations could be approximate. Translation chains were not always preserved. Memory had to carry an extraordinary experience across long intervals before investigators wrote it down. That does not make the testimony worthless. It changes what the testimony can responsibly do. A remembered direction can help constrain a reconstruction. It is not a measured trajectory. A description of sequence can support comparison between accounts. It is not a stopwatch. A reported injury or death cannot be turned into a final count when the underlying historical record remains incomplete. So the first task is not to combine every account into one cinematic fireball. It is to separate what was observed when it was recorded and how much precision survived the journey between those two moments. The second problem was not what people remembered. It was when scientists could examine the ground. According to NASA's historical overview, Leonid Kulik attempted to reach the region in 1921 and reached the main devastated area in 1927. That broad chronology is enough to mark the delay. The important point is not to turn the expedition into an adventure story. It is to understand what the delay did to the evidence. By the time major field investigation began, Tunguska was no longer a fresh event site. Investigators were reading a landscape years after the event, while also relying on testimony recorded after the fact. The delay did not erase the evidence. It changed the kind of evidence available. Later expeditions expanded systematic measurement, including the directions of fallen trees. The forest became a physical archive, but it was an archive without event-time instruments at its center, without an accepted recovered main body, and without a complete record of every change that occurred before the surveys began. A fallen tree has a direction. Many recorded directions can become a map. That sounds like a direct route back to the explosion. But the map and the reconstruction are not the same thing. The measured azimuth of a trunk is field evidence. The position of an explosion center is an inference. A proposed flight path is an inference. A burst height is an inference. An energy estimate is an inference. The mapped Tunguska footprint is structured, but it is not a perfect radial circle. Its irregularities matter because a real forest is not a blank sheet of paper. Terrain, tree type, local exposure, and the moving source of the blast can all affect what later appears on a survey map. Even the famous standing, stripped trees near the central region do not function as instruments that directly display an altitude. They become constraints only after a physical model explains how a moving airburst might produce one pattern on the ground rather than another. This is the crucial distinction, the forest recorded consequences. Scientists must work backward from those consequences toward a cause, and more than one combination of path, height, fragmentation, and energy can sometimes reproduce parts of the surviving pattern. The forest is therefore one of Tunguska's strongest witnesses, but it is a witness that speaks through models. The evidence did not end at the forest. Seismic records, pressure wave records, optical reports, and other atmospheric observations form additional evidence classes. In principle, they can constrain the timing, scale, and behavior of the event independently of the fallen trees, but each record has its own claim ceiling. A seismic signal does not convert directly into one explosive yield. That conversion depends on a source model and on assumptions about how energy coupled into the ground. Reports of unusual night skies were associated in time with Tunguska, but the mechanism behind them cannot be treated as settled. A distant instrument can narrow possibilities without identifying the object's composition or fixing one burst altitude. These signals matter because they may test the forest-based reconstruction from another direction. They do not matter because one dramatic trace contains the whole answer. When the evidence classes are considered together, atmospheric airburst remains the strongest broad framework. A cosmic body can enter the atmosphere, deform, fragment, and deposit enormous energy before a conventional surface impact occurs. Under that framework, the lack of a normal impact crater is not a contradiction. It is an expected possibility. The framework also explains why the event cannot be treated as a stationary bomb suspended at one height. A moving body carries momentum downward. Its energy can be released across a path rather than at a single observed point. Modern hydrocode work shows why point source scaling can misrepresent the ground effect of this kind of event. This is why Airburst leads. It accounts for the event class and the broad pattern of destruction without requiring fringe explanations. But the framework has a boundary. It does not tell us by itself whether the body had one exact composition. It does not choose one trajectory. It does not turn modeled altitude or energy into direct measurements. Airburst is the strongest starting answer because it explains the broad event. It is not the final answer to every detail inside it. The most direct way to identify an incoming object would be to recover it. Tunguska offers no accepted recovered main body that can provide a direct composition measurement. That absence does not prove that the object was a comet. It does not prove that it was an asteroid, and it does not mean that every physical trace claim must be ignored. Some studies have reported unusual elements or microscopic grains from the region and interpreted them as possible Tunguska material. Those claims remain source-specific and disputed. Their value depends on provenance, chronology, contamination controls, comparison samples, and independent replication. They are not equivalent to a confirmed fragment. Many modern reconstructions use an asteroidal body as an assumption, but an assumption that helps a model reproduce damage is not the same as a recovered fact. Composition also cannot be reduced to a label. Density affects mass. Porosity affects how a body deforms. Mechanical strength affects when it fragments. Velocity changes kinetic energy. Entry angle changes the length of the atmospheric path. Each choice alters where energy is deposited and what damage reaches the ground. That is why size is not an isolated measurement waiting to be read from the forest. A diameter estimate is the output of a system of assumptions. Different combinations of density, strength, porosity, velocity, and angle can change the size a model requires to reproduce selected parts of the observed damage. Without an accepted main body, object properties remain constrained indirectly. Tunguska can tell us what kinds of bodies might fit. It cannot hand us one physical specimen and end the argument. The same problem appears when scientists try to reconstruct the path. Witness locations and reported directions can provide lines of sight. Fallen tree orientations can provide a ground pattern. Neither is a direct recording of the body's complete flight through the atmosphere. A line of sight is not a trajectory. A tree direction is not a trajectory. Both become trajectory evidence only after geometry, coordinate conventions, source selection, and model assumptions are applied. This matters because the witness record was assembled at different times with different levels of location precision. It also matters because forest-based reconstructions can depend on how investigators define the center, account for irregular terrain, and model the moving blast. Published reconstructions therefore infer candidate paths. The surviving evidence does not force one exact azimuth, one exact entry angle, or one clean arrow labeled as the true route. That uncertainty is not a minor cartographic problem. Change the path and the body travels through a different amount of atmosphere. Change the angle and fragmentation may begin under different conditions. Change the velocity and the same assumed mass carries a different kinetic energy. Trajectory is not one line placed on top of the reconstruction. It is one of the variables that reshapes the reconstruction from the inside. This is why Tunguska's exact-looking numbers cannot be separated from one another. Start with composition. That influences density, porosity, and strength. Those properties affect the mass assigned to a body of a given size. Velocity and entry angle then shape the atmospheric path and the dynamic pressure acting on the object. Fragmentation changes the energy deposition profile. That profile changes the effective height and direction of the blast reaching the ground. The resulting forest footprint is then used to infer the energy that may have produced it. The reasoning runs in a circle of constraints. Even the phrase burst altitude can refer to different things. One study may mean the onset of major fragmentation. Another may mean peak energy deposition. Another may use an effective source height chosen to reproduce ground damage. Those values cannot be merged as though they measure one identical point. Energy has the same problem. Incoming kinetic energy is not automatically the energy deposited in the atmosphere. Deposited energy is not automatically the fraction coupled into blast at the ground. A TNT equivalent estimate is a conversion, not an instrument reading, from 1908. Different model families handle these steps differently. Pancake models, debris cloud models, cascading fragmentation models, hydro codes, and probabilistic ensembles can use different assumptions and still reproduce selected evidence. Some can be calibrated to the same modern event with different parameter choices, then diverge when scaled to Tunguska. So, when one reconstruction produces a different height or yield from another, the disagreement may not begin with the final number. It may begin much earlier in the assumed material strength, the fragmentation rule, the entry geometry, or the definition of what counts as Tunguska-like damage. The numbers move together because the model is solving a coupled system. Precision at the end cannot be stronger than the assumptions at the beginning, several reconstructions can describe one historical event without having equal value in every respect. Older point source scaling offers a simple comparison, but it can miss the momentum and distributed energy deposition of a moving body. Fragmentation models explore different ways the object may deform and break apart, but their coefficients and strength assumptions are not uniquely fixed. Hydrocodes model the flow physics in greater detail, yet they remain simulations, not historical replays. Probabilistic ensembles make non-uniqueness visible, but their results still depend on prior assumptions and on the damage criteria used to select acceptable cases. The correct comparison is therefore not which model looks most realistic or which one is newest. It is which evidence each model uses, what it assumes, what it reproduces, and what remains unexplained. Across these differences, several conclusions remain strong. A destructive atmospheric event occurred. Airburst is the leading event-level framework. A conventional crater is not required. The forest is a major physical constraint, and the detailed reconstruction depends on models. What does not remain fixed is the exact object, path, breakup sequence, altitude, or energy value. Several reconstructions, one event. A robust framework without one uniquely recovered history. Tunguska is not wholly solved, and it is not wholly unexplained. Known: a major destructive event occurred over the region in 1908, and the forest preserved a powerful physical record. Strongly inferred: a cosmic body deposited destructive energy in the atmosphere, making airburst the leading broad explanation. Model-dependent: the object's detailed properties, its path, fragmentation history, effective altitude, and energy. Disputed: physical traces claimed as possible Tunguska material. Unresolved: which single reconstruction, if any, most closely matches the lost event? Some distinctions may eventually prove irrecoverable if no surviving independent record can test one model against another, but the entire event is not unknowable. Airburst explains the event class. It does not recover one unique object, one unique path, one unique breakup sequence, or one final number. That boundary is not a failure of science, it is where responsible reconstruction ends.